The two factors it depends upon is known as mass and velocity. You have to understand that momentum is actually of two kinds. One is angular momentum, one is linear momentum. When a ball is coming towards your hand, you'll actually feel that force. The cricket ball is pushing onto your hand, so you can actually feel that force. Whatever will be the initial momentum of a body, that will be equal to the final momentum of the body. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, Mysuru. And we were dealing with laws of motion or simply Newtonian mechanics. So let's dive right into it. So in the Newton's second law of motion, we actually saw that second law stated that force applied is directly proportional to rate of change of momentum. And we didn't actually know what this momentum was, and I didn't actually explain what this particular quantity entails. So this equation can be later written down as F is equal to ma, which is stated as Newton's second law of motion. But what exactly is that? What exactly is that particular momentum? Just like how mass is the determining factor for inertia, we can actually quantify an object in motion. That is, if you want to quantify how much energy, or not energy, but simply how much a substance is going in motion, how much energy it can impact or impart, we can actually quantify that using momentum. Momentum can be generally said to be mass times velocity. So momentum can generally be said to be mass times velocity. It is generally used to quantify the motion of any object. So just know that, just imagine it like this. If there is any mass, any body that is having the mass m and it is in motion or it is moving with a particular velocity v, then we can say that that particular body will attain what is known as momentum. So this quantifying of this particular movement is known as momentum. So remember that simply momentum just means that any moving object that is having a particular mass will have momentum. And the two factors it depends upon is known as mass and velocity. How large the object is and how fast the object is moving. Those two are the determining factors that influence momentum. Remember, momentum is actually a vector quantity because it has velocity in it, which means it has a particular direction and a phase value. So momentum is also a vector quantity, and the unit of momentum is nothing but kilograms, and the second unit is velocity, that is meter per second. So the unit of momentum is nothing but kilograms meter per second. So again, momentum is indicated by the letter P. So capital letter P with a vector symbol on top of it will indicate momentum. And you have to understand that momentum is actually of two kinds. One is angular momentum, one is linear momentum. In this particular chapter, we will only be dealing with linear momentum. That is momentum that is tied to an object that is moving in a straight line. That is known as linear momentum. If at all that particle is going in a circular path, then the momentum will become angular momentum. So right now we are going to deal with linear momentum, or simply a particle which is moving in a straight line. So the equation for linear momentum, or just P, is equal to m times v, where m is mass and v is the velocity of the object, and P is equal to mv is the magical equation that will give you the momentum of any object. So if an elephant is going with 5 meter per second speed, that is, let's say an elephant is weighing 1000 kilograms and it is walking through the jungle very slowly, it will still have a larger momentum. That is because even though the velocity is very small, 5 meter per second or like half a meter per second, the mass of the elephant is very large, which means that 1000 times 5, which is equal to 5000 kilograms meter per second. So it is having a large momentum. But does that mean that only heavy objects having a small velocity or large velocity will be influencing momentum? Not exactly. If there is a small bullet, very small bullet, but it is traveling at a high velocity, then the damage it can impart is very high. That is because even though the mass of the bullet, let's say, is 50 grams or 1 kilogram, let's say for calculative reasons, For easiness, let's say there is a bullet which is weighing 1 kilogram. And that particular bullet is traveling with a speed, phenomenal speed of 500 meter per second or 10,000 meter per second speed. Then obviously the momentum is even more than that of an elephant. That is because even though the mass is really small, the velocity factor is 10 times bigger, 100 times bigger than that. So just because of that factor, the bullet will have a larger momentum. So even if the bullet is weighing only 1 kilogram, but the velocity of the bullet is 10,000 meter per second or 1000 meter per second, or let's say it is 10,000 meter per second, then what will happen? Then the entire momentum is even more than that of an elephant, which is moving really slow. So it is not just the mass, it is also the velocity that is influencing the total output, that is influencing the momentum of any object. You have to understand that either mass or velocity can together influence momentum. If mass is more and velocity is more, the total momentum will be high. If mass is low and velocity is low, momentum will be low. But they can be balanced by if one is high and one is low, and vice versa. So that is all about momentum. So now you understood that there is something known as momentum, and that is possessed by objects in actual motion. That is, when object is moving, and any object that is having a mass m is actually moving, that particular object will have momentum in it. So that particular body which is in motion will have momentum. Now, what does this particular momentum have to do with everything we are going to see? So we just saw that rate of change of momentum is actually proportional to force applied, which means that the rate of change at which momentum varies depends on the force we are applying, because velocity is actually related to that. And again, is there anything more to this particular momentum? Yes, there is. What if an object having mass m is traveling with a velocity v and the velocity suddenly changes? Then we can say that since mass is not changing, let's say a cricket ball is coming towards you really fast and you want to catch that particular cricket ball, then what happens? Initially, that particular cricket ball which is having a mass m is coming towards you with a velocity v. But once you catch the ball, what happens? The mass of the cricket ball still remains the same. It is still m. But what happens to the velocity? It decreases. If it initially came at 10 meter per second, now it's at 0 meter per second, or maybe it's at 2 meter per second. So what happens? The velocity actually changes, which means there is a change in momentum. Momentum actually changed from an initial value to a final value. So why is this change important? The change is important because we are going to monitor this change and observe a really interesting fact, that is, momentum is actually conserved. So what does this conservation means? We'll get to that very soon. But for now, let's focus on the cricket ball that I just caught. So the cricket ball I just caught, what is that? So we can just simply say that the cricket ball was just a mass, that is m, traveling towards me with an acceleration a. Or simply, I can simply say that cricket ball is a body that is exerting a force. And let's say this is my hand. Let's say this is my hand. I'm reaching out and I'm grabbing the ball. It's a very bad painting, but yeah. I'm reaching out and I'm grabbing the ball like a catch. So what happens? A really high force is coming towards my hand and it is immediately stopping. So I can say that mass m moving with an acceleration a, that is ma, F is equal to ma. Or simply you can also say that mass m is moving with a velocity v, because change in velocity is actually known as acceleration. So I can also say that mass m is moving towards my hand with a velocity v, but once it reaches my hand, the velocity changes. So I can say it is acceleration also. Ball is accelerating towards my hand. The velocity is changing at each second. Anyways, just imagine that a ball is coming towards my hand and I have caught that particular ball. So obviously, since this ball is traveling with the velocity or it has an acceleration, I can say that this particular cricket ball exerts a force onto my hand. You can actually feel that force. When a ball is coming towards your hand, you'll actually feel that force. The cricket ball is pushing onto your hand. So you can actually feel that force. So a force is exerted onto my hand. A force is exerted onto my hand. But is it for like 5 minutes? Is it for like 10 hours? Is it for like an entire day? No. The force is only experienced for a small amount of time. Let's say just delta t. Delta indicates small changes, or dt is also fine. We can also indicate it using dt. So a force is being experienced for a very short period of time. Let's say for 0.5 seconds or 1 second or 2 seconds or something like that. So when this particular force is being experienced for a short period of time, then that particular thing is known as impulse. So we can actually define impulse as a strong force, or simply a force which is experienced for a very short duration of time is known as impulse. So we can actually say that impulse is nothing but force which is experienced for a very short period of time. That is known as impulse, indicated by the letter I, and the equation for I is nothing but F delta t, or you can also write it as F dt. So force which is acting for a very short period of time is known as impulse. That is how a cricket ball which is exerting a force onto your hand feels. That is how if your best friend punches you in your face, so that punch will only last for 1 second or 2 seconds. So that particular punch is nothing but impulse. That is a force that is being experienced for a very short period of time. That is known as impulse. So this is one way of representing impulse, that is force that is acting for a very short period of time, that is known as impulse. But there is also one more method of representing impulse, that is change in momentum. That is the change in momentum del P, delta indicating change or very small. Here it is delta very small, that is T2 minus T1. It is a very small time gap. Here also it is indicating change or simply final momentum minus initial momentum. So we can actually say that this is actually equal to final momentum minus initial momentum. So PF is indicating final momentum and PI is indicating initial momentum. Or simply we can, biologically we can actually say that if a mass is initially moving with a velocity v, and then it changed to u, or simply we can say that it was initially moving with the velocity u. Initial velocity is usually represented by u. So initially it was moving with the velocity u, later it changed to v. So we can see that the difference is this one, mv minus mu. When you take the mass inside, we can actually write it as mv minus mu. So we know that mv is nothing but momentum, that is final momentum, and this is initial momentum. So we can just say that change in momentum is also known as impulse. We can also have one more equation, that is change in momentum, to indicate impulse. Again, there too momentum is coming up, right? There momentum was showing up in Newton's second law, momentum was showing up. Why is momentum showing up everywhere? So the reason is that momentum is actually an innate property of every mass. Any mass that is in motion will have momentum. And one more important thing is that that particular momentum will be conserved. Conservation of momentum, all you have to understand for now is that initial momentum will actually be equal to final momentum. That is, no extra momentum is gained by the body. No extra momentum is lost by the body. Whatever will be the initial momentum of a body, that will be equal to the final momentum of the body. Or simply saying, it is another way of saying that momentum is actually conserved. So what it actually means in scientific terms is that if two bodies are colliding, that is, two bodies are hitting with each other, which means one body will be in rest and the other body will be coming with a velocity v. So mass m2 is actually at rest and mass m1 is actually coming with a velocity v. So what happens when this object hits the object which is in rest? What happens is that the momentum of the first incoming body is transferred onto the second body. So you can actually see this physical example as the examples of Newton's cradle, or simply known as Newton's balls. That is, there is an arrangement where you can see multiple balls will be hanging like this. So if you swing one ball to the left and release it, what happens is that this ball will impact this ball and this ball will impact the next ball, and remember, only one ball will be swinging to the left. So if I release only one ball from this side, only one ball will be moving to the left. That is because the momentum of this particular ball was transferred to this particular system, and that particular momentum was carried out here. So what it actually means is that how much ever momentum I'm giving to this particular system equal, that is, if before collision I'm giving m1 v1 momentum, after collision also the momentum will be m1 v1. That is, if mv is given here, mv will be distributed outside. So for example, what if I take two balls? If I take two balls and release it, what will happen? Okay, there is only one ball remaining here, which means the only one ball will be moving to the left. No, the important fact, experimental proof is that if I am giving the momentum of two balls to this particular system, what happens is that one ball here will stay in rest and the remaining two balls will actually move to the left. You can actually watch this. You can actually prepare this. This is known as Newton's cradle. So when you actually release individual balls, if only one is released, one will go to the left. If two is released, two will go to the left. If three is released, three itself will go to the rest. So this is actual proof of conservation of momentum. If a mass which is moving with the velocity v imparts that momentum to another system, then momentum before collision and after collision will be equal to each other. That is simply saying that momentum is conserved. It is not lost anywhere. It is not given out in any other forms. It is conserved purely, truly, and always. So that is conservation of momentum, given that there is no external force applied. If there is external forces in play, that force can influence the momentum of the object or the system, and there can be variations. If no external force is applied, then the net momentum will be conserved. You don't believe me, right? I know you don't believe me, so I'll do one thing. I'll just prove it to you. So the proof of conservation of momentum is very simple. Conservation of linear momentum. So here the proof is very simple. Imagine that there are two bodies having masses m1 and m2. So there are two bodies having masses m1 and m2, which is having initial velocities. That is, initially they were traveling with a velocity of u1 and u2. And they are coming together and they're going to collide. So what will happen? When they collide, their velocities or their momentums will change. So what will happen then? The new velocity they attain right now, I'm going to call it as v1 and v2. Imagine that two masses are coming together with a velocity of u1. When they hit together, they go in their separate ways, but now this particular direction is changed, which means they are having new velocities. They are coming together with initial velocity u1 and u2. They are colliding together. They move away with new velocities, which is indicated as v1 and v2. Their masses do not change, but their velocities change, which means there is a net change in momentum. So I am assuming that all of this, that is, this particular two bodies coming together, colliding and going in different ways with different velocities, happened in a very short period of time. Just like the snooker table or pool, 8-ball pool, where you hold a stick, you aim at a ball, and you just like flick the ball. Or playing caroms, where you keep the striker and you just flick the striker and the striker will hit the next coin. So it is collision of two bodies. Just imagine it like that. The striker will be moving with a particular velocity and it will be hitting one coin, and then the striker will be moving away with a new velocity. Just like that, two bodies coming together, hitting and moving away with different velocities. And all this happened in a very short period of time. That is, the collision happened for a very short period of time. It's not like they collided, they stayed together for like 5 minutes or 10 minutes and they went apart. No, it is only for like a fraction of a second. So I'm assuming that it happened in t amount of time, then I can actually say that the force experienced by that particular object generally, that is generally F is equal to ma, or simply I can say that F is equal to m v minus u divided by t, because v minus u by t is nothing but acceleration. So I'm going to write it m into v minus u by t. Now, for first body, that is for the first body which is having mass m1, I can write it as m1 v1 u1 divided by t, because t is common for both. The collision happened in t amount of time. Now generally for body 2, I can write it as m2 into v2 minus u2 divided by t again. Now this is from Newton's second law of motion. From Newton's second law of motion, I can actually write that F is equal to ma, or simply F is equal to m v minus u divided by t. Now this is force on first body, this is force on second body. Now there is one more thing that is going to be in play here by Newton's laws. We took the second law, first law is already in effect. Now we have to also consider Newton's third law of motion, that is every action has its own equal and opposite reaction. So if this force is equal to this force, then I can actually say F is equal to minus F2. So from Newton's third law of motion, I can say F1 is actually equal to minus F2. Those forces will be equal but opposite in direction. When the collision happens, it will go in different ways. So the forces will be experienced in opposite directions, and let's assume that the forces are equal. So then I can actually say that m into v1 minus u1 divided by t will be equal to m2 into v2 minus u2 divided by t, and the minus sign here. So opening these brackets and cancelling out the similar quantities, t and t will get cancelled. So m1 v1 minus m1 u1 will be equal to minus m2 v2 plus m2 u2. Now, taking all the minus signs or all the final velocities and initial velocities together, I can actually write it as m1 v1 plus m2 v2 is actually equal to m1 u1 plus m2 u2, or simply this is momentum of the first body and this is momentum of the second body, and that is the initial momentum and this is the final momentum. On the right hand side you have the initial momentum of the two bodies, here you have the final momentum of the two bodies. Generally we can say that mv is equal to mu, or simply pi or pf is equal to pi. That is, initial momentum is actually equal to final momentum. When two bodies actually collide with each other, we can say that from Newton's second law of motion, F is equal to ma, or simply acceleration is equal to v minus u by t, or simply for the writing in terms of two bodies and rearranging, we can actually say that m1 v1 plus m2 v2 is actually equal to m1 u1 plus m2 u2, or simply final momentum will be equal to initial momentum. That is the proof for conservation of momentum. You're not believing that, okay, momentum is not conserved, all you said is rather unclear. So I'll do one thing, I'll show you an application of conservation of momentum. So I'm going to show you an application of conservation of momentum. What would you like? Let's take a bullet being fired from a gun. So imagine that I have a gun like this. So imagine that I have a gun like this and there is a bullet inside this particular gun. So I'm going to consider this entire gun and bullet as one system for now. So what is the momentum of this particular gun and bullet? Is it running anywhere? No, right? It is not running anywhere, it is not moving anywhere. So actually the momentum of this particular gun and bullet is actually zero. That is because even though the system has a mass, the problem is that there is no velocity here. Velocity is actually equal to 0, which means the entire momentum is actually 0. If an object is not possessing velocity, we can actually say that the momentum of that particular quantity is 0, because momentum is actually a way to quantify motion. So here it is 0. But the moment the bullet is being fired from the gun, the moment this bullet leaves this particular gun and moves forward, what happens? The gun and the bullet gains momentum. Because again, if I'm holding a gun like this and I'm firing a shot, what happens? The bullet is actually moving forward and the gun is actually coming backwards. Now you might have figured it out. The application and analysis of conservation of momentum. Why does the gun have to come backwards when the bullet has to go forward? That is because of conservation of momentum, because momentum of the bullet should match with the momentum of the gun. So since they have different masses, the bullet will actually travel at more higher speed, but the gun will also move backwards because momentum should be conserved. If you are considering the entire system, momentum of the bullet should be equal to momentum of the gun moving backwards. Let's say that this entire arrangement of gun and bullet initially, which is at rest, when the bullet is not being fired, we can say that initial momentum of the system can be said to be initial momentum of the bullet plus initial momentum of the gun. So initial momentum of the bullet plus initial momentum of the gun. So let's indicate it as Bi and Gi. So the initial momentum of the bullet is in rest, so it's 0. The initial momentum of the gun is also at rest, so the initial momentum is 0. Now what about the final momentum? So final momentum, that is Pf. Pf will be equal to, again it will be the final momentum of the bullet plus final momentum of the gun. Okay, Bf and Gf. If I assume that the bullet is having a mass of m1 and is traveling at a velocity of v1, then the gun will be having a mass of m2 traveling with a velocity of v2. V is because it is final velocity, because initially u was 0 for both the terms. So we don't have to calculate that because this will be actually equal to 0. Now the final momentum will actually not be equal to 0 because it is having velocities. So what will happen again? If I fire the gun in slow motion, you can see that the bullet is going forward, the gun is coming backwards. So the motion is relatively opposite in direction, right? So to indicate opposite direction in physics, we will actually say, or we will actually use negative signs. So we can actually say that gun is traveling backwards compared to the motion of the bullet, or simply gun is traveling in the negative direction compared to the bullet traveling in the positive direction. If you consider a graph like this, then you can actually say the bullet is traveling in the positive x direction and the gun is coming back in the negative x direction. This coming back action or going in the negative direction is actually known as a recoil of the gun. So this particular phenomenon, conservation of momentum in the terms of gun and bullet, can be simply said to be, it is a recoiling of the gun. Gun is recoiling back because of conservation of momentum. So we are going to calculate that as an application. Okay, since no external force, I am not applying any force, nor is Superman coming and applying any force, which means that the net external force applied on this system, the system is again gun and the bullet, is 0, which means that momentum before and after should be equal. So before we actually know it is 0, which means we can actually write it as, we know that momentum before should be equal to momentum after, which actually means that 0 should be equal to PBF plus PGF. or we can actually say that momentum, that is m1 v1, that is m1 v1 should be equal to minus m2 v2. Why minus? Because I simply took one of the terms to the left hand side. So I can actually say that momentum of the gun should be equal to final momentum of the bullet. So m1 v1 will be equal to m2 v2. Or rearranging, we can actually say that v2 is equal to m1 v1 divided by m2. So what does this actually prove? This application actually proves that momentum is conserved, one. And the second thing is that if you ever want to find out what is the recoil speed of a gun, then you can use this particular equation. That is, if I know what is the weight of the bullet and what is the speed of the bullet, then I can actually say what is the recoiling effect of the gun. That is how we calculate. If we are holding a pistol, we can actually hold it like this because the recoil is very small. But if you are firing an AK-47, you can't hold it far away from the shoulder because the momentum will be large. The velocity at which the gun recoils will be large. It will just knock off your shoulder. That is why when you're firing AK-47s, I don't know if you will, but if you're firing one, you will be keeping it very close to the chest because the recoiling speed will be very high. And this equation will help you in order to figure out what is the recoiling velocity of any gun. And there is a minus sign here. There is a minus sign here, I forgot. The minus sign just indicates that relative to the bullet, the gun is coming backwards. Or relative to the gun, the bullet is moving forwards. It is just indicating direction. So what we did was very simple. We considered the initial momentum of the system, which is actually the sum of the initial momentum of the bullet and the initial momentum of the gun. Since there is no velocity, it is 0. Then we took the final momentum. Final momentum will actually be equal to Pf plus Pf of the gun and bullet. That is, if it is traveling with m mass and v velocity, it is m1 v1, and the gun will be traveling backwards with m2 mass and v2 velocity. Or simply we can actually say that since net momentum is conserved, we can actually write it as initial momentum will be equal to final momentum. So since initial momentum is 0, 0 will be equal to final momentum. Final momentum can also be written as m1 v1 plus m2 v2. Rearranging, we can just say that m1 v1 will be equal to negative m2 v2. Or again, from that, if I want to know what is the velocity of the gun or the bullet, I can just rearrange the equation and find out what is the velocity of the gun recoiling or the bullet traveling. Anything can be found out using this particular equation. So we just proved that momentum is conserved, and we just showed that the application level principle, that is the recoiling effect or recoiling velocity of a gun, can be found out using this particular equation. That is all in today's session. So we learned about what is impulse, what is momentum, what is conservation of momentum, and two important things. One is conservation of momentum's proof when two bodies are colliding, and one more important thing is that the application level where we find what is the recoiling velocity of a gun. So I hope you have understood everything. I'll come back with a new session with a lot more to learn. Thank you.